Vice here, and today we'll be talking about the lines. So we have learned the basic operations of vectors. We have learned the definition of vector addition, subtraction, scaling, right? We have also talked about the various type of products that can appear when you use vectors. We have talked about the dot product. We've talked about the cross product. We've talked about its properties and its applications in calculating area, distances, length of projections, and so on. And so it's time to start constructing in more interesting objects from these vectors, and we'll be learning how to define a line using a vector. So simply, what is a line, right? A line in 3D space is a collection of points. So a line is a continuum of points, right, in this 3D space. And what could it represent? It could, for example, represent a light ray. It could represent the laser beam. Yeah, because all of those things travel in a straight line. So one way, right, to represent a line, a rather naive way to represent a line would be to write a collection of infinitely many points, right? So we write the coordinates of infinitely many points, and that would actually describe a line. But of course, it's how do we can't write infinitely many points on paper, right? Um, so we need to think of a smarter way to get about doing that, and and we can use vectors actually. So let me just illustrate what I mean. So let's say we have a line, right, which we want to define. Let's say we have 1 point on a line. In this case, the point is 1, 2, 3. So the point A lies on 1, 2, lies on the line, and let's say we have another point on the line, which is, let's say, F, right? So let's say this point is 3, 4, 5. So do you realize that if we have the vector, right, from one point on the line to another point on the line, then actually we can actually scale this vector to travel along the line. So what I mean is that you see that point F, right? If we scale the vector along uh, with we scale the vector with any real number, we'll be moving along the line by the virtue of the fact that the line is a straight line, right? That goes from that goes on forever. So if we scale it by any number, we'll be hitting all the for any real number that we scale it by, right? The directional vector would will be traveling along the line. So that's the key idea. So yeah, so we define a line by first specifying one point on the line. In this case, let's say it's A, right? And then after that, we specify a directional vector. In this case, it's the B vector. And then we let the directional vector scale along the line. So by trying out different real numbers, right, we're traveling along the line. And so let me just show you what I mean by that. So so we can describe the line by in a sense, we can describe a line by two vectors. One is the position vector of any point on the line. In this case, we have chosen A to be the point on the line, and the other vector is a directional vector which is parallel to the line. Remember, we talked about parallelism in the previous video. It's parallel to the line, and if we scale by any amount, then we can traverse along the line. So yeah, so to define the line, right, we need two vectors. One is we write it with we denote any point on the line with r equals to a, right, which is the point, 1 point on the line, plus lambda b. So what is this lambda, right? But before we go to lambda, the b is called the directional vector. And the lambda, now let's go to lambda. Lambda is any real number. So what does this equation say? This equation is saying that any point on the line, or rather the collection of all points on the line, is described by first telling us 1 point on the line, and then choosing a particular value of lambda and using that lambda to walk along the direction of the line. So what this looks like is, let's say we have this line, right? and let's say we have the origin here, and then we have the point A. So point A is a point on the line, is A, and then this is, let's say, the point we want to describe. So this is F. So this will be the R. Okay, perhaps I should call this R. Yeah, okay, let's go ahead and call this R. So and this is, the B is like this. So the B is any directional vector that is parallel to the line. Parallel to the line. And by scaling it up by a lambda, by any real number, we can use this directional vector to traverse along the line from point A, right? And so we go from OA will give us 1 point on the line. Then by reaching here, we can now travel along the line by using the scaled up version of the directional vector. So in this case, perhaps it's like perhaps lambda, so for lambda equals to 1, it'll be this, and for lambda equals to 2, perhaps it'll be at R, and lambda equals to 3 will be somewhere else here, and lambda equals to 4 is here, and then lambda equals to 0 will be a point A, right? Lambda equals to -1 will be some other point here, and by varying lambda across all real numbers, we are having a continuum of all the points in between and spanning that across the entire line. So do you see that the real cleverness of defining a line this way is that instead of specifying an infinite amount of points on the line, infinitely many coordinates, right? We can just specify two vectors to define the line. One is the any point on the line. In this case, we've just chosen 1, 2, 3, right? And then the next thing we need to specify is any directional vector. In this case, we have chosen, in this case, the directional vector we could choose is, let's say, 2, 2, 2, or it could also be 2, 2, it could also be 1, 1, 1. But as long as any directional vector parallel to the line, then and then we let the lambda do the infinity part, because lambda can be any real number. So there's an infinitely many real numbers. So the lambda will describe the continuum, whereas to specify the line, we just need to provide two vectors. So that is the definition of a line, and yeah. So with this definition, let's go about understanding some properties of it. So the first thing is first thing is if we want to check if an unknown point f lies on the line, we can write it as OF equals to the A plus lambda B, and try to solve for a unique value of lambda. So what I mean by this is, let's go through an example, right? So for example, in the case of our visual here, we have our A is 1, 2, 3, and our B goes to 1, 1, 1. So if we want to check if the point, let's say we want to check if the point 3, 4, 5, right? If we want to check if, let's say, OF, or let's say we want to check, the question is 3, 4, 5 on this line, this line, which is the R equals to A plus lambda B for lambda in real numbers. Okay, so is this point on the line, we'll write it as 3, 4, 5 equals to 1, 2, 3 plus lambda 1, 1, 1. So looking at the first one, looking at x coordinate, right? Looking at x coordinate, we have 3 equals to 1 plus lambda, and that gives us lambda equal to 2. So we just need to substitute into the y coordinate, right, to make sure that it holds true. So 4 equals to 2 plus lambda, it also gives us lambda equal to 2, and the z coordinate as well. So there will be 5 equals to 3 plus lambda, that also gives us lambda equal to 2. You see that all of them have the same value of lambda. There's one common value of lambda that satisfies this equation. In fact, we can solve it from one of the axes, one of the coordinates, and plug into the rest to check. And if this value of lambda is found, then that means yes, the point F lies on this line. However, if we change the question slightly a little bit, right, let's say we put 3, 4, 6, then if the question is 3, 4, 6, is there one value of lambda that satisfies this equation? And the answer is no, because there's for x and y coordinates is lambda equals to 2, but for z coordinate lambda equals to 3. So no, it's not a common value of lambda, so the point does not lie on the line. Okay, so that's for the equation, that's for checking if a point is on the line. Yeah, so sometimes question will ask that, right? Sometimes they might ask if a point is on the line, and that's how you check it. So second note about lines is that if the line L, right, if the line L passes through 2 points C and D, then any scalar multiple of CD can be used as the directional vector B. So what this means is that if you have a line L, right, and let's say it passes through points C and D, then the vector CD is like this. But if you want to pick out a directional vector of the line, you can choose any scaling of CD. So it can be this, it can be much longer than CD, right, or it can be in the opposite direction as well. As long as it's any scalar multiple of that, then it's valid. And that's because when we define the line, right, as R equals to A plus lambda B, then this can be any real number, right? So if we have any scalar multiple of B, because lambda already spans across all real numbers, right, this term already scales up from the very, very far to the negative to the very, very far positive. So no matter how we scale B, right, we can choose any one of them, and the line will still be defined because lambda will span from minus infinity to infinity. Okay, yeah, so that's that. And additionally, right, point 3 is that any choice of point A on line works too. It works too. So what I mean is that if you have the line, then you can choose any starting point. So you can choose this as your A. So you can choose this as your A also. All of them are valid choices, and the reason is because the directional vector B will bring you along the line. So if you choose, let's say you have made this choice of the A, right, then if you have chosen this A, then you can get to this A by just adding it to a scalar multiple of B. So by using the directional vector B, we can walk along the line, and yeah, so that's that. So in the next video, we'll be learning more things we can do with the line, and namely we'll be talking about finding the foot of a perpendicular from a point onto a line. So let's say we are given a line and we want to find how to get from a point to the line, right, the closest distance, the projection onto the line, right, you find how to find this point, and as well as we'll be talking about parallel lines and how lines interact with each other. So if not, that's all for this video. Have a nice day. Bye.